Hello, thanks for inviting me to the workshop and for making this happen. I really wanted to participate in person, but alas. So this is a part of the large joint project with Dmitry, Damir, Ryan, Josiah, and Alex. So what do we do? Well, we try to optimize for multivariate energies. I'm going to show only the spherical case, although some notions and ideas could be used for other situations as well. So we're going to optimize over a set of barrel probability measures on the unit sphere. And at the same time, we're going to work with the finite configurations as well. So a natural definition of the energy is just summing up the values of a potential over all possible endpoint subsets of our set. We do not exclude here the diagonals, so we allow points to coincide. And the optimization question then is to try to optimize the energy given the dimension, the number of points, and our potential. And the measured theoretic counterpart is more or less the same. Just integrate your potential over all endpoint configurations taken from our probability measure and try to optimize given the dimension and the potential over all probability measures. Now, well, why is this interesting? Why do we do that? First of all, there are actual applications where multi-point multivariate potentials are used. Second, a bunch of nice geometric notions actually are inherently multivariate. Say any sort of potentials that are based on volumes, areas, or something like discrete curvatures, Menger curvatures, something like that. They're all based on multivariate potentials, so it kind of makes sense. And the third reason is when you have a hammer, you're always in search of nails, and we do have a bunch of hammers to tackle something like that. What else? Yeah, I formulated two problems, general problems, in the discrete one, the one for measures. But of course, if you know something for measures, then you immediately conclude something for discrete sets, because you can always take a measure based on delta functions, uniform distribution over a finite set, and vice versa. If you know some optimization properties for all finite sets, then of course you can extend it to measures by approximating the measure by finite sets. So I'm kind of gonna hop between the two during my talk, so hopefully it's not as confusing. So sometimes I'm going to show some inequalities for measures, sometimes I'm going to write them in terms of finite sets. All right. So let's start with 2-point energies and 2-point bonds. Well, the two classic potentials that we want to base everything on are Riesz potentials and p-frame potentials. I'm going to write everything in terms of scalar products because it's going to be more convenient. So what we're going to do, we want to try to show something for multivariate potentials that are immediate generalizations of Riesz potentials and p-frame potentials. So this is what we're going to do. Well, how would you? What is the general method of finding lower bounds for a bunch of energies, going back to the method of Delsart, Udin, the paper of Konkumar mentioned here several times already. Well, if you take a sequence of normalized Gegenbauer polynomials in dimension d, and I've written the first three because we're going to use them. Then the integrating the value of this potential over for any measure, any probability measure, and actually any signed measure on this sphere as well, we must have a non-zero number, a non-negative number. So this is the basis for the linear programming method, but actually I don't write here linear programming because SDP also sits here. The semi-definite programming also sits here, if you write it this way. Well, if we take the polynomial of degree 1, the Gegenbaur polynomial of degree 1, which is just f of t equal t, right? Then this is what we're going to get, and this is kind of obvious. It's also can be considered as the positive definiteness of the Gram matrix, if you like. The equality in this case happens when the measure is balanced, meaning that the center of mass of our measure is at the origin. So this is what you get for k equal to 1. For k equal to 2, so what happens if k is 2? Then the measure is what's known a frame. The energy is what's known a frame energy, right? So define it as 2 frame, but in the literature it's known as just frame energy. And if you use the polynomial, yeah, just in case, this was the polynomial. So if you use this one, then you would get the following inequality. The measures where the equality happens are known as isotropic. If in the discrete case, the sets are also known as tight frames. And if you combine the two, the degree 1, degree 2 conditions, then it's a balanced tight frame, which is also known as a spherical 2 design. And we have already seen a bunch of spherical designs the previous week and 2 days ago. What else? The second inequality in the discrete version can be also written this way. If you have endpoints, yeah, I should probably write it somewhere here to have more space. If we have endpoints and we summon them up this way, then it's going to be at least n squared over t. And this is also what I'm going to use in one of the next slides. All right. So this is what happens for 2-point bounds. Just a bunch of simple examples. So how can we extend something like that to multivariate, to the multivariate case? Well, we're going to use the kernels that were used by Vlasiuk and Valentin when they found out the method, the semi-definite programming method to apply it to finding bounds for kissing numbers. So the general idea is the following: if you fix one point on the sphere and you project points of your set or even a measure on an equator with respect to this point, then you get a set or a measure in the codimension 1. And you can use the very same 2-point bounds there in the codimension 1 case. So it's roughly like this. If you have a pole here and you have a couple of points, then you can project them here. So if this is y, this is z, we're going to have normalized projections, y bar, z bar, that live in the space of codimension 1. And then you can use the very same bounds there. So how does it work practically? Well, this is the inequality that that works for. I write here again for a finite configuration, but of course you can modify a little for measures as well. So just to copy the picture. So x, z, y, and we project it here and there, z bar. So what we have here, this guy is it's just a scalar product of y bar and z bar. And then why does the inequality work? Well, if you can say that mu of y bar, the measure of this point, is just p of u1 minus u squared, okay, over 2, and the same for mu of z bar is p of v 1 minus v squared, okay, over 2. So you can think about it as this measure inequality we had for 2-point bonds in the previous law. Well, now here the summation is for y and z, right? You can sum up for x as well and take x from our set. Still, nothing's wrong with that. Still, the inequality is correct. And so what kind of polynomials I want to use just for demonstration purposes in the talk. So I'm going to use the following three kernels. So the first one is the case where P is a Gegenbauer polynomial, is the Gegenbauer polynomial degree 2. And for dimension d. And K0, so this is the case K0, this is the case K1, and this is the case K2. And the second case is Y1, where I use the first degree polynomial for P and the first degree polynomial for Q as well. And the Y2 is the case where I use the 0 degree polynomial for P and the second degree polynomial for Q. Okay. So what happens is that when you integrate, when you look at these kernels, Y0, Y1, Y2, when you integrate them over a sphere, you should get a non-negative number. You should get a non-negative number. And this is what we're going to use. Okay. So any questions so far? Because I want to go to some examples, I guess. All right. So, well, these kernels are non-symmetric, so it totally makes sense to symmetrize the whole thing. So I'm going to go over all the permutations of x, y, z, 6 permutations, and I'm going to get I'm getting symmetric kernels as 0, as 1, as 2, and they're written here explicitly. They're written here explicitly. So again, the whole point is that for these kernels, if you integrate it 3 times for any measure, you should get a non-negative number. Okay. So I want to show several Tau examples first, before moving to something more complicated. So this is a reasonable geometric multivariate potential. Let's say we have 3 points on the sphere, right? And we look at the squared volume of the tetrahedron that is based on the origin and these 3 points. What is the best measure that we can choose so that the average volume squared is maximal possible? So it's a fairly reasonable problem from the geometric probability. And it appears that using these kernels, Bashak kernels, we can answer this question quite easily. So look at the volume squared. It's just a determinant of the Gram matrix. So this is the expression we get, and we can expand it using our kernels. So as you can see, in this expansion, we just have a constant, and these 3 kernels are described with negative signs. So when we integrate it, the first term is going to give us a constant, and all the other terms are going to be non-positive. So naturally, this is the bound. So this is the bound for the average volume. When does the equality hold? Well, this should happen when the integrals over for S0, S1, S2 are all vanishing, and it's fairly easy to show that this happens for all isotropic measures. So this is a necessary and sufficient condition for that. So that's the first example. In the same manner, we can work with the squared area of the triangle. So again, we have some measure in the sphere. We choose 3 points with respect to this measure. What is the best choice for this measure to have the maximal possible average squared area for the triangle? And write down the area in terms of scalar products of our 3 points, x, y, z. And then we can expand it using the kernels, the Marshall-Planck kernels. And I don't write it here because there are more terms, a bit longer. But of course, when you integrate, all the terms here are going to be with the negative sign, though, apart from the first constant term. So when you integrate the whole thing, you should get something that is no greater than 3 times d minus 1 over d. The terms that are going to show up here are not just for isotropic measures. There's going to be a couple of terms that are vanishing for balanced measures as well. So the necessary and sufficient condition for the optimizer is going to be balanced and to be isotropic. Okay, so these are two toy examples how it may work. Well, so we would like to tackle a more general question, of course. So let's say we have a multivariate potential that is the square of the k-dimensional volume based on k points. So again, it's we take the origin, choose the k points with respect to our measure, right? And we want to figure out what is the maximal possible average volume squared. And this problem is already resolved by Cahill and Casazza. So why do I write Rankin here as well? As a matter of fact, in one of the papers, Rankin covered the case d equal to k. Both proofs, both in the Rankin case and the general case by Cahill and Casazza, are linear algebraic. So Rankin just uses the Kashibin theorem. Cahill and Casazza a little more difficult, but not that long actually. And yeah, they don't show it for measures. Their proofs are for finite sets, but of course, the work for measures is just the same. So, well, we wanted to extend this result to the case of area squared. So let's say for the generalization of this area multivariate potential, we're going to take the square of the k minus 1 dimensional volume that is based on k points chosen on the surface of a sphere with respect to a given measure. And as a matter of fact, we did prove that we did find the maximum of the energy with respect to this potential, and figured out all the maximum points. So the equality holds if and only if the measure is balanced and isotropic. Here I don't include k equal to 2 though, because for k equal to 2, it's even simpler than that. So what is the general idea in the proof? How we prove this stuff? Well, I don't want to go too much into detail. So as a matter of fact, if you write down this potential, the squared volume, k minus 1 dimensional volume of k points on the surface of a sphere, then you can expand it in a bunch of volume squared potentials of Cahill and Casazza, plus a bunch of kernels that are the generalized Bashok-Wellington kernels that were initially that they appeared in the work of Musin. I wrote here for k points. I think it's for k minus 2 points to be honest. And those Musin kernels are vanishing on balanced isotropic measures, and the kernels of Cahill and Casazza vanishing on isotropic measures. So altogether, we get the set of optimal measures as balanced isotropic measures. All right. So this is what we get for those measures based on volumes. Now I want to switch gears a little. As one of the classic potentials in one of the first slides I mentioned, the p-frame potential. So we would like to figure out something like that for many points. So this is, as a matter of fact, a potential that we would like to study. A fairly reasonable generalization of p-frame potentials. So here we have a product of 3 scalar products based on 3 points. And it appeared to be fairly complicated though. So I want to show the case of p equal to 1 only, and even that is not resolved completely. So what happens with the case p equal to 1? Well, first of all, let's try to explain the problem without using the absolute value, which doesn't help in a sense of p-frame potentials completely, because you're going to change the power here if you don't use the absolute value. So this is the dilemma. Let's try to explain it using the kernels we already had before. So here we have the product of 3 scalar products, and I want to explain why it's at least 1 over d squared. There are a bunch of different ways of doing that though. So this is definitely not the only way, but I want to show it in the spirit of the machinery that we use. So we can expand the scalar product of the product of 3 scalar products using the potentials I described in the previous slides, right? S0 and S1 with the positive coefficients. Also there u squared, v squared, t squared show up. So what do you do with these guys? Well, these guys are just frame energies. So if you have this, then it's at least 1 over d. So each of them is at least 1 over d. So this is what you get: 3 over d here, and then minus 1 over d squared, and that's exactly 1 over d squared. And of course, these guys are non-negative. So yeah, the equality happens when measures are isotropic. We already talked about this for S0 and S1, and of course, u squared is precisely the frame potential. So it must happen for isotropic measures exactly. All right, this is not exactly what we want, right? So we want to study this one frame energy. So what is the difference? Well, the difference is that we have the absolute value here. So the exact equality to 1 over d squared may happen if the product of 3 scalar products is always non-negative, because otherwise our one frame energy is going to be larger than that. So well, clearly we do have measures like this, right? It's no problem. Let's say take a measure that is based on an orthonormal basis, for instance. Then the product of 3 scalar products is never negative. But the problem is, how would we even start describing all measures that that satisfy this condition? So we did that for the case of dimension 2. So if everything happens on this circle, then we can actually describe all the optimizers. As I have already said, the uniform distribution over an orthonormal basis is going to work just fine. But as a matter of fact, 2 orthonormal bases are also going to be fine. So we have a uniform distribution over one basis over the second one, and we can take them with any positive coefficients. Now this measure is going to work. And as a matter of fact, all optimizers are like that. So the equality holds only in these cases. Well, since we solved the problem for p equal to 1, then it gives us some information for other values of p. As a matter of fact, if p is from 0 to 1, then the inequality is just the same. Well, how so? It just fairly straightforward that this is at least UVT to degree 1, and the equality happens if and only if the value if and only if UVT is 0 or 1. So it tells us that, well, 2 orthonormal bases are not really possible. The minimizers, the only minimizer is the uniform distribution over 1 orthonormal basis. Yeah, I haven't said that, but of course, these potentials are projective in nature. So we take everything up to central symmetry. All right. Okay, so having this goal in mind, right, to describe the minimizers for the 1' energy. So and the whole description depends on this, right? Let's simplify our problem a little. So here we have a condition that the product of 3 scalar products is non-negative. Well, what if we require the product to be exactly 0 for 3 distinct points? Now, if 2 of these points coincide, say x is equal to y, then surely we have a non-negative number. It's just a square of a scalar product. So we just need to take care of the cases where 3 points are distinct. So why we require the one of the 3 scalar products to be equal to 0? And well, not very surprisingly, it appeared to be the problem of Riesz, who asked what is the maximal set of non-zero vectors, so that for any triple there are 2 orthogonal vectors. And in the literature, such set is called almost orthogonal. Well, so this problem was actually resolved in 1992 by Rosenfeld, who explained why the size of any almost orthogonal set is no larger than twice the dimension. So it appears that the machinery that we have on our hands can explain this as well. So I want to show you the proof of the theorem of Rosenfeld, and actually something a little more general than that, using the kernels that the Bashok-Wellington kernels essentially. So here's the theorem. Note that this condition is not exactly what we want in our problem for 1' potentials, because for 1' potentials we would like it to be non-negative. Here we can prove the result for non-positive case, which covers the case equal to 0. All right, so let's try to explain where this all comes from. So I'm using the same kernels as before. I write them here explicitly. So these are kernels S0 and S1. And if I write them down and take a proper linear combination, then actually this term is going to disappear. So what is left in our sum, or now integral, if you like, if you take this this combination? Well, we're going to have a triple product. So I guess I should move the slide. So we're going to have a triple product right here, and we have a term with the sum of squares of scalar products. Now, for the next step, let's say the size of our set is n. By the way, so far there was no explanation why the set is finite, but it's fairly straightforward to explain. Say quadratic bound is pretty obvious right away, because the number of points that are orthogonal to a given one can be bounded by induction, and then the number of points that are not orthogonal to a given one is no greater than the dimension. Anyhow, so what do we get? What do we get here? So in this sum of triple products, well, if x, y, and z are distinct, then this should be no greater than 0. So we can disregard them without changing the validity of the inequality. What happens if some of them coincide? Well, in case x is equal to y to z, then this is what's going to show up. So for all those diagonal triples, and in case x is equal to y not equal to z, this is how the sum looks like. And we have to take 3 of them because we should work with all 3 cases: x equal to y, y equal to z, x equal to z. So this is the inequality that we get this way. Now, what is left in this inequality actually is just the frame potential, the frame energy, right? So this guy is the frame energy. Now, if the coefficient for the frame energy is positive, then so I should write probably here. This is positive if n is less than 3/2 d, which is already good. We're already good, right? So this coefficient should be negative then. But then if it's negative, we can substitute our frame energy by its minimal possible value, which is n squared over d. And if we do so, the inequality we get this way is precisely n is no greater than 2d. So that gives us the result of Rosenfeld. In fact, something a little more general. Well, so how can we use something like that? Even trying to describe those minimizers. So those were almost orthogonal sets. So what about the sets that we get by this result of Rosenfeld? Well, first of all, our proof shows that they must be tight frames, right? Because the frame energy is precisely n squared over d. So they actually do solve our optimization problem. So they do give us the minimizers for the 3.1 frame energy. Now, looking at our result for dimension 2, right? We figured out that all the minimizers for the 3.1 frame energy should be unions of 2 orthonormal bases. Those unions of 2 orthonormal bases are going to work in this case as well. So they're still good. The question is, are they only minimizers that we can get this way? Are they actually only solutions of the Erdős problem? And as a matter of fact, no. So that's a bit surprising, but starting from dimension 5, there are other sets of size 2d that satisfy the Erdős condition. So it's really hard to describe the solutions of the optimization problem, even in this case. So even if you relax the condition, even if you require the scalar product to be 0 for 3 distinct points, still not clear what to do next. So there's still a lot of it is open here. All right. So I want to formulate a bunch of questions that we're interested in regarding all this. And first of all, this is essentially what we started with, and we still haven't resolved the question. So if you have if your potential is just the volume, not volume squared, but just the volume, it seems natural that the maximization happens if the measure is uniform. It does look like that. And as a matter of fact, the conjecture is true for 2 points. So if you have 2-point potentials, then this is definitely true. If you have an area of a triangle based on the origin and 2 points taken on the sphere, or you just have a length of the line segment for the 2 points on the sphere, then the optimizer is the uniform measure. Now, why doesn't it work so far? The reason why it works for k equal to 2 is that you can actually expand your potential as the sum of Gegenbauer polynomials with positive coefficients. And then the measure the integral should vanish for all Gegenbauer polynomials. So the uniform measure is the only measure that's going to work this way. Unfortunately, when you try to expand something like that for k greater than 2, or 3-point, 4-point potentials, the kernels that we work with, they don't give us the expansion. So this whole method doesn't really work. So something like that, something different should be applied here. What else? So for a bunch of potentials that we work with, either they show that optimizers must be discrete, or at least they do have discrete optimizers. Well, what about the discreteness here? Do we necessarily have discrete optimizers for potentials like that? Must we have discrete optimizers for potentials like this? Say if we have the volume not squared, but the volume for some other degree, volume cube, volume to 3/2. Seems like that should work, but we have no idea though. And I also want to add that the possibility of numerical experiments is kind of limited because it's hard to optimize for multivariate energies for many points. It's really hard. The number of terms becomes large very fast. What else? This is something that should be tackleable. So I said that starting from dimension 5, those Rosenfeld sets are not necessarily unions of 2 orthonormal bases, but for dimensions 3 and 4, it actually works. So there is a chance that they form the only optimizing configurations for 3.1 frame energy, and subsequently you can get the result for t less than 1 right away. Now we figured out how to use semi-definite programming bounds, right? Those kernels of Vlasiuk and Panichin to solve this old problem of Riesz, to give it another solution for the old problem of Riesz. And this old problem is actually one of the initial problems for orthogonal representations of graphs. So, well, there is a good chance, since there's a good chance to get something else in this direction, because now we have a more or less industrial method, semi-definite programming that can cover cases with the more intricate conditions on graphs, rather than just having the condition of having an edge in every triangle, which was our condition for orthogonality. So maybe something else is going to show up in this direction. And this is actually all I wanted to show you today. Thanks again.